In this episode, we're going to step into serverless computing, which is one of those cloud ideas that sounds simple at first and then surprises people once security is involved. The word serverless does not mean there are no servers. It means you do not manage the servers directly, and that changes where security work lives. In a traditional setup, teams worry a lot about patching operating systems and hardening host configurations. But in serverless architectures, the cloud provider handles much of that layer. The risk does not disappear. It shifts, and the shift is what creates confusion for beginners. The real attack surface in serverless is not a single machine you can lock down. It is the combination of function code, identity permissions, event triggers, exposed endpoints, and the services your functions can call. If you misunderstand that surface, you either overtrust the platform and get exposed through permissions and triggers, or you treat serverless like traditional servers and miss the places attackers actually exploit. The goal here is to build a clear mental model of what serverless is, where its attack surfaces truly are, and how you secure it by designing boundaries, permissions, and visibility around the parts you control. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is defining serverless in a way that maps to security thinking rather than marketing language. Serverless usually means you deploy small units of code, often called functions, and the cloud platform runs them for you when certain events happen. Those events might be an incoming web request, a message arriving in a queue, a new object being written to storage, or a scheduled timer firing. The platform handles scaling, runtime management, and the underlying compute infrastructure, which reduces your direct responsibility for host patching and capacity planning. What you still own is the function code, the configuration of triggers, the identity under which the function runs, and the permissions that identity has to other resources. You also own how data flows in and out of the function and how errors and logs are handled. Beginners sometimes assume that because the provider manages the runtime, security is largely handled, but serverless security is less about the host and more about the glue that connects services together. The glue, meaning triggers and permissions, is where many real-world serverless incidents begin. To understand the attack surface, it helps to think in terms of entry points and trust relationships. An entry point is any way an attacker can cause your function to run or can influence what data it processes. A trust relationship is any permission or connection that allows your function to access other services, such as reading from storage, writing to a database, or calling a management API. In serverless architectures, entry points often multiply because functions are easy to create and triggers are easy to attach. A single application might have dozens or hundreds of functions, each with its own trigger and its own permissions, which means the attack surface can grow quickly if governance is weak. Trust relationships can also be broad if teams grant functions large permissions for convenience, and once a function is compromised, those permissions become attacker tools. The real danger is not that serverless is insecure by nature, but that it is easy to accidentally create a wide web of implicit trust. Beginners should remember that attackers love webs of trust because they make lateral movement easier. One major serverless attack surface is publicly exposed endpoints, because many serverless applications include functions that respond to web requests. If a function is reachable from the internet, then it is subject to the same threats as any public service, including credential abuse, injection, business logic abuse, and denial attempts. The difference is that serverless scaling can make abuse cheaper for attackers and more expensive for you, because the platform may scale to handle the load, and you pay for execution. Another difference is that the function environment is often ephemeral, meaning it starts and stops quickly, which can make certain kinds of persistence harder, but can also make troubleshooting and visibility more challenging. The defensive mindset is to treat any public serverless endpoint as a public application surface that needs strong authentication, careful input validation, and monitoring for abnormal patterns. Beginners sometimes think of serverless endpoints as safer because they are managed, but if the endpoint is open and the function logic is weak, attackers can still exploit it. The platform can run your code reliably, but but it cannot guarantee your code makes safe decisions about inputs and outputs. Event triggers are another major attack surface, and they are less intuitive for beginners because they do not look like classic network exposure. A trigger might fire when a file appears in storage, when a message arrives, or when another service emits an event. If an attacker can influence that trigger, they can influence when your function runs and what it processes. For example, if a function triggers on storage events, an attacker who can write objects to that storage location can cause the function to execute with attacker-controlled content. If a function triggers on a message queue, an attacker who can publish messages can feed it malicious payloads or create floods of events. This is why trigger permissions and input boundaries matter so much, because the trigger is effectively the doorway into your function. Beginners often focus on who can call the function directly, but in serverless architectures, many functions are not called directly at all. They are called indirectly through events. If you do not secure the event source, you do not secure the function, because the event source becomes the attacker's handle. Identity and permissions are often the highest impact serverless risk surface because functions frequently need access to other services, and teams often overgrant those permissions. A function that processes images might only need to read from a specific storage location and write to another, but in practice it might be granted broad storage access across the environment because that was quicker to get working. If the function is compromised, the attacker can use that broad access to steal data, modify data, or destroy data. Another common mistake is using the same identity across multiple functions, which increases blast radius because a weakness in one function becomes access to everything that identity can touch. Least privilege is particularly important for serverless because functions are small and focused by design, which means their required permissions should be narrow and easy to define. Beginners should internalize that serverless does not reduce the importance of IAM. It often increases it, because permissions become the main way attackers expand their reach. When you lock down function identities tightly, you turn compromises into contained events instead of cascading disasters. The function code itself is an attack surface, but the risk is less about server management and more about application logic and dependency behavior. Functions often rely on third-party libraries and package dependencies, and those dependencies can carry vulnerabilities or malicious behavior. Because functions are frequently deployed quickly and frequently, dependency risk can spread fast if there is not good discipline around what is included. Another risk is improper handling of inputs and outputs, such as trusting event payloads too much, returning sensitive information and errors, or failing to enforce authorization checks before performing actions. Serverless code may also handle secrets, like API credentials, and if secrets are stored insecurely or logged accidentally, an attacker can extract them. The key is to treat serverless code as production application code with the same safety expectations as any other application, even though it runs in a managed environment. Beginners sometimes assume that small functions are simpler and therefore safer, but small code can still be dangerous if it has powerful permissions or processes untrusted inputs. The attack surface is not only the lines of code, it is the combination of code and the power it is allowed to wield. Another real serverless attack surface is inter-service connectivity, because serverless architectures are often built as many small components that call each other and share data. If one function can call another, and that second function has broader permissions, an attacker can pivot through internal calls to reach higher privilege. This is similar to lateral movement in traditional systems, but it happens through service calls rather than through network hops between servers. A common design pitfall is trusting internal calls too much, assuming that if a request comes from inside the environment, it must be safe. In reality, if one internal component is compromised, internal trust becomes the attacker's advantage. Secure serverless design encourages you to authenticate and authorize internal calls as carefully as external ones, and to limit which components can call which others. It also encourages clear boundaries, where a function that handles untrusted external input is not the same function that has direct access to sensitive data stores. Beginners should see that micro-level separation is a strength of serverless, but only if you actually separate trust and privilege, not just code files. Observability and logging discipline matter in serverless because the environment is dynamic, and without good telemetry, it can feel like actions happen in a fog. Functions may spin up and down quickly, and large systems may execute many functions per second, which creates a lot of events to interpret. Attackers can exploit gaps in logging by probing triggers, causing failures that are not captured well, or abusing permissions in ways that look like normal service calls. A secure serverless posture includes capturing execution logs, trigger events, identity context, and outcomes in a way that supports anomaly detection. You want to notice patterns like unexpected invocation spikes, unusual invocation sources, repeated failures that suggest probing, and functions accessing resources outside their normal scope. Logging also matters for cost and availability abuse, because serverless can be targeted with traffic that forces expensive scaling. Beginners should remember that serverless reliability and serverless security overlap heavily, because the same signals that show abuse often show operational risk. When you can see what is running, why it is running, and what it is touching, you can respond before small misuse becomes a bigger incident. A major beginner misunderstanding is believing that serverless reduces security responsibility so much that you can ignore hardening, when the truth is that it changes the hardening targets. You still need hardened defaults, but the defaults are now about function permissions, trigger constraints, network reachability, and safe integration patterns rather than about host firewall rules. You still need stable configuration through updates, but stability now includes keeping triggers scoped, keeping identities least privilege, and ensuring new functions are created with safe templates. You still need to protect administrative access, because control plane changes can create new triggers, broaden permissions, or expose new endpoints. If an attacker gains control plane access, they can create a new function with broad permissions and a hidden trigger, which becomes a powerful persistence method. This is why serverless security must include control plane governance, because the ability to define functions and triggers is itself a high-risk capability. Beginners should understand that serverless reduces some operational burdens, but it does not reduce the need for clear security boundaries. It may even increase it because the environment can change quickly. To secure serverless architectures effectively, you want a design that limits entry points, limits trust, and makes behavior visible. You limit entry points by ensuring public endpoints exist only when necessary, and when they do, they are protected by strong authentication and careful input handling. You limit trust by scoping triggers so only the right event sources can invoke functions, and by scoping permissions so each function can touch only what it needs. You design boundaries so that functions that handle untrusted inputs do not automatically have high privilege, and you avoid broad shared identities that turn one flaw into many. You make behavior visible by enabling strong logging, monitoring for anomalies, and treating permission changes and trigger changes as high-signal events. This approach does not require you to memorize specific platform settings to grasp the concept. It requires you to think of serverless as a network of small, powerful components connected by triggers and permissions. When those connections are tight, serverless can be both flexible and secure, but when those connections are loose, the attack surface grows in ways that are hard to see until something goes wrong. To close, securing serverless architecture starts with understanding that the real attack surface is not the hidden servers you do not manage, but the exposed triggers, the reachable endpoints, the function identities, and the service-to-service trust links that you define. Public endpoints invite classic web threats and cost abuse if they are not constrained and monitored. Event triggers can be exploited if attackers can influence the event sources, turning normal automation into attacker-controlled execution. Over-permissioned identities are one of the fastest ways to turn a small code weakness into broad cloud compromise, which is why least privilege is central to serverless security. Internal trust paths can enable lateral movement if internal calls are not authenticated and authorized with the same care as external ones. Observability and logging discipline provide the evidence you need to detect misuse in a dynamic environment where execution is constant and distributed. When you design serverless with tight entry points, tight permissions, and clear visibility, you keep the benefits of the model while reducing the risks that attackers actually exploit, which is exactly what good cloud security architecture is meant to achieve.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.